Okay, now we're going to take on the topic of MTI cancellation. And we're going to be going through a general description, look at Doppler ambiguities and blind speed effects, and the MTI improvement factor. Now first let's look at the general waveform that we're going to be using. And this is similar to what you've seen before. But what I want to do is I want to go over in detail how we define all of the terms of either an MTI or a pulse Doppler waveform. For an MTI waveform, there would be 3 bursts of pulses, or 2 or 4, and that would be about the number. For pulse Doppler processing, there's going to be a lot more. But let's just go look and see how the numbers are, the quantities are interrelated in the symbology that we'll be using. First, let's start with an individual pulse. Here we see the envelope of a pulse of sine waves, and that length of that pulse of the envelope is capital T. That is the pulse width. And 1 over T is the bandwidth of the signal. And here we have TPRI, which is the time between this quantity, which is called the pulse repetition interval. Makes sense, okay? And the frequency of these pulses is the pulse repetition frequency, which is 1 over the PRF, which is 1 over the PRI. So, and that pulse repetition frequency, the PRF, is we also call F sub P. Now the duty cycle of the radar, which is the fraction of the time that the radar is turned on, is capital T divided by the time between pulses. So it'd be T over T sub PRI. And T C sub P is the coherent processing interval, that amount of time that we're coherently processing a group of pulses over, coherently. And that would be just N times the TPRI times the time between each pulse. And N, of course, is the number of pulses in the coherent processing interval. And N is usually 2, 3, or 4 for MTI systems. And N is much greater, 8 to 10 to up to thousands, 10,000 sometimes, and even more for pulse Doppler systems that we're going to be talking about. So there you have the nomenclature. Now for an airport surveillance radar, these are the numbers, generally speaking, and to order magnitude in airport surveillance radars, no matter which one you grab. The pulse length is about a microsecond, and the bandwidth is 1 over that of megahertz. The time between pulses is approximately a millisecond, and 1 over that is a kilohertz, the PRF, the pulse repetition frequency. And the ratio of those two quantities is 0.1%. Many radars will operate up to 5 or 10% duty cycle, but airport surveillance radars and many operate at these low duty cycles of the order of 0.1%. The coherent processing interval of the ASR9 is 10 pulses. It's an airport surveillance radar. And some airport surveillance radars operate in the MTI mode, and they'll use 3 pulses coherently, and then the next 3, and then the next 3, and then they'll non-coherently add the results of those. So, but the coherent processing interval for airport surveillance radars in an MTI mode would be 2, 3, or 4. And N is, as I said before, for pulse Doppler radars, it can be as little as 8 up to 10,000, up in the tens of thousands, and sometimes even higher. Now I want to look at a two-dimensional visualization of how the data is collected. It's a two-dimensional visualization. And let's just go back and look at what those pulses we sent out. And let's assume we're looking at, just for our example, the data collection for an MTI radar that coherently processes 3 pulses. So we'll ignore this section of that diagram we saw. Now, what we're doing is each of these dots stands for a sample of time after the pulse was sent out. And the time when we get back that sample is twice the range divided by the speed of light. So for each sample, and let's just pick the 13th sample, in each pulse, it'll have the same time delay from the transmit of each pulse. And therefore, that 13th sample, let's say for instance, is looking at a range of 4.6 kilometers. So that sample of 13 corresponds to about 4.6 kilometers for a radar that's on this view graph, the sample. We're going to take these 3 pulses and we're going to integrate them. Let's look at them. Now, the way they come in is they come in with all of the samples. So the data is collected this way. Then we go back, and from the next pulse, pulse number 2, we collect this data. And then from the next pulse, we collect this data, and on and on and on, till we've collected 3 for a 3-pulse canceller, or 10 for an airport surveillance radar that's using pulse Doppler mode, or 1,000s. If it's airborne radars, usually will deal with PRFs way up in the thousands or tens of thousands. But notice the data is collected this way. But when we process the data, we're going to need the data for each range cell. We're going to need the data this way. So we're going to have a memory, which in the radar acronym business we call a corner turning memory. And this memory that we're going to use is, we'll use solid state memory. So what we'll do is we take in the data, send it through an A to D converter to digitize it, both the real and the imaginary parts. And we could store those real and imaginary parts. We could store them in one memory for the real and one number for the imaginary. Or we could store a complex number in some format in the data. But what we're getting here is the complex envelope of the received waveform for the entire range out to here, out to the next pulse begins processing. And for that 3-pulse canceller, you say at this range, 13 range gates away, here are the 3 pulses that we want to process through an MTI canceller. Now let's look at range ambiguities. We noticed that we collected data at 13, but there was some limiting number because there's going to be a time when we send out the next pulse, and we can't be receiving while we're transmitting. But there are ambiguities in range that take place because of the pulsed nature in range and the pulsed nature in Doppler. And first I want to go through the range ambiguities. So let's look and see. We've got a transmit pulse, and at range R1 away, we have a pretty large target. And then after a while, we transmit another pulse, and we'll get a detection in that same range cell. But if there happened to be a target this length away, plus that 13 range pulses, we get in the same range gate the one returned from 2 different targets that's equal to R1 plus what we call the unambiguous range. And that unambiguous range is called RU, and it's C times the time between pulses divided by 2, and that's equal to C over twice the PRF. So range ambiguities and range ambiguous detections occur when echoes from one pulse are not all received before the next pulse. And also, close-in targets that are clutter can mask very weak targets because of the R to the fourth, R to the sensitivity of the radar falls off as without any extra talk on my part. We'll talk later about it. If the sensitivity falls off as 1 over R to the fourth, the smaller target in blue could be masked by a near in clutter that's at the same ambiguous range. Okay. Now let's look at the range rate, the radar range, and the choice of the PRF that we choose. Here's a graph which just shows you the unambiguous range, the vertical axis, and notice this is a logarithmic scale in nautical miles. Plotted as a function of, well, speed of light over 2 times the PRF. And here's the PRF on a log scale. You see it's a straight line on a log scale. It goes inversely proportional. For an airport surveillance radar of the class we use these days, 8s or 9s, the range we want to see out to is about 60 nautical miles. And if we want an unambiguous range of 60 nautical miles, we go over here and we see we have to keep the PRF about 1250 hertz or less to have unambiguous velocity detection, Doppler velocity detection. And that 1250 hertz corresponds to about 150 nautical miles. Airplanes are a lot faster than that. And so the PRF is going to be, this is an ambiguous PRF. So let's start at the top over here with the bullets. The unambiguous range, as we've shown you, is inversely proportional to the PRF. If the PRF is too high, second time around clutter can be an issue. So that is to say, if we set the PRF at 5 kilohertz, we'd have, as was shown in the previous U graph, we'd have ambiguous, we'd be ambiguous in range. Now let's look at how we suppress that clutter. And for this example, I'm going to show you as a pictorial example of clutter. I'm not showing you any rain clutter. Let's start with a simple clutter. And what this is a PPI display. We've talked about them before, but I'll just briefly remind you. What it is an analog display, which the gain is set so that targets just above the noise level of the receiver, you'll see white dots. So these aren't noise detections. They might be 5 sigma noise detections because there's a fluctuation. Noise is a random process. But you see black, no targets are there. And the targets we see here are clutter. These are the buildings at Atlantic City. People are pouring their money into the slots. And these are, the buildings very close, the ground. And as I said before, I think these are the detections all very close of the towers and a high tension wire. And up in here are a few targets. If you looked from scan to scan, you see they move in a little pattern, which you'd recognize from scan to scan as that of a moving target. Well, we'd like to do something pulse to pulse to suppress the clutter. And we're going to use a high-pass Doppler filter. And this is the simplest high-pass Doppler filter, a 2-pulse MTI canceller. And what we're doing here is we're taking the input data, those, say the first, we're not going to use 3 pulses I showed you before in that. We're just going to use 2 pulses. And as you can see here, well, if you have a ball bearing out in space that's a foot in diameter, and it's not moving, and it's connected to a non-conducting rod up in the sky, this is a Gedanken experiment, a thought experiment, you'll get an echo over that ball bearing. That's sphere. And you send the next pulse out, since it's spherically symmetric, you're going to get the same echo exactly. So what would happen is if you sent it through, one pulse through, at that one range gate, where that ball bearing was located, and you subtracted from it the next pulse at that same range gate sample, you're going to get zero output. So this ideally, in an ideal sense, if you set up a 2-pulse MTI, that's what you get. You get zero out for non-moving targets, and you get an output where there's a moving target. Now, another type of display, which in very early operators, or if you work with radars and you put a scope up and you want to see if the MTI circuits are working, you can look at the IF pulse and then the next one. And what you'll see is for non-moving targets, like right here, and we're looking at the complex return. One of the real or imaginary parts of the complex return, because the part that's going to move is the phase. You kind of have an amplitude sine theta, amplitude cosine theta, And so what you're going to do is between pulse to pulse, the target that's moving with a Doppler velocity will change, as it does from here to here and from here to here. Real targets are there, but here and here, they're like that fictitious ball bearing, ground, the Trump Center, here to here, the buildings along Atlantic City, the towers, the high-tension towers that carry electricity into this area, the ground at the lower lobes of the antenna sees and the side lobes, and tall buildings, chimneys from power plants, which are in this area. Tens of miles across, they won't move. But an airplane will, and will give you a return. And what it will tell you is that the target is moving. It won't tell you that the target's not moving. These are. Now, for a moving target indicator processing, and this is just an ideal case for ground clutter. We've got the ground clutter, which is very narrow, but it will have some modulation to it. And in the case of a rotating antenna, the amplitude modulation of the pulses as they go by a fixed object, like that imaginary sphere in space, it's going to be amplitude modulated by the gain pattern of the antenna. That amplitude modulation will result in the frequency spectrum of that non-moving clutter, a spread, which has to be taken into account when we start looking at suppressing clutters 4, 5, 6, 7, 8 orders of magnitude, 80 dB for the engineers, physicists by training. So what we want to do, to go back to the original theme, is to notch out the Doppler spectrum occupied by stationary clutter. Provide a broad Doppler passband everywhere else we can. And notice that at 1 over the time between pulses, we get a phenomena called blind speeds. Blind speeds occur at multiples of the pulse repetition frequency, that's Doppler frequency, which corresponds to a Doppler velocity. So, and that is an artifact of sampling the PRF. You will always have blind speeds unless you sample the PRF high enough. But we showed you before, if we sampled the PRF high enough, we get range ambiguities. And here we're going to have Doppler ambiguities. So we're going to be caught between a rock and a hard place. And we're going to, as we move on, we're going to show you how to deal with these. So when the sampling frequency, the PRF, equals a multiple of the Doppler frequency, we have a fact called aliasing, where these all fold down under one another. You can't tell. In some radars, if this corresponded to 0 and this corresponded to 100 knots radial velocity and this 200 knots, if the target was at of what the Doppler spectrum would look like of a typical radar, and this is the true two-pulse MTI canceller frequency response. And notice the aliased clutter spectra too. That aliases also. And I haven't forgotten, targets can be coming or going. So over to the other side, we've got targets that are going minus 10 knots with 100 knot blind speed will occur as a bump at 90 knots. And a minus 190 knots will appear also at minus 90 knots, multiples of the PRF. Now this frequency response of a two-pulse canceller is just given by twice the sine of pi times the Doppler frequency times the time between pulses. And that's for a two-pulse MTI. And if you want to derive this, it's Skolnick's third edition. I'll save that for later because this, he spends an enormous amount of time on pulse Doppler processing and MTI filtering, but we'll go back. And also, I alluded to the basics of how you do this stuff in the digital signal processing portions that were upfront tutorials for those who are not familiar with it. Now, the clutter spectrum, what's the reality? The clutter spectrum has a finite width, which I told you, which depends on the antenna motion if the antenna rotates. For a phased array radar, there wouldn't be this clutter spectrum because phased array radars move so quickly. They'll move in microseconds, send out a burst of pulses. Move in microseconds, burst of pulses. So you won't have that antenna motion. The motion of the ground backscatter, forested vegetation, which will, the forest in the wind will give you some spread, and also instabilities in the transmitter will contribute to the clutter spectrum having a finite width. And all MTI processes see some clutter spectral width, and you saw some of that in the ground clutter. There was like a spike, and then there was this breadth, and that was maybe in the range cell, an object that didn't physically move, but moving trees also. All of these have their strengths and weaknesses, these different kinds of MTI processors. The different kinds I haven't mentioned yet. There are 2-pulse, 3-pulse, 4-pulse cancellers. A 3-pulse canceller is just you take the residue from a 2-pulse canceller, pulse 1 and 2, and then you do another 2-pulse canceller with 2 and 3, and then you subtract those residues. And that is a 3-pulse canceller. 4-pulse canceller, you do the same thing. The coefficients become just the binary coefficients when you take, say, x plus 1 parentheses, or x minus 1 parentheses to the nth power, and where n is for a 2-pulse canceller 1, etc., etc. And you can use feedback in MTI canceller design. I'm going to show you one of those in a minute. And all of these different cancellers have strengths and weaknesses, but the main issue is much clutter backscatter leaks through an MTI canceller. And one reason it's going to be is rain is there, and it's a big clutter problem. These don't handle rain very well at all. And that amount of the clutter that leaks through the filters we call clutter residue. Okay, now on to Doppler ambiguities and blind speed effects. Well, we talked a bit and alluded to Doppler ambiguities. Now let's look at pulse Doppler waveforms. And in a pulse Doppler waveform, samples the target at the PRF. Now say we take a target with 0 radial velocity. It's just going to be a constant number, and we sample it at the sample time at 1 over the PRF, or the T sub PRI. We're going to get a constant number. If a target is moving at the blind speed, you're going to get the same constant number. So you can see that sampling gives you that blind speed. You can't tell from the samples that you've got a sine wave if you sample at integral multiples of that. In this case, the sine wave is 3 times the unambiguous velocity, which is lambda times the PRF divided by 2. Okay? And this sampling causes what we talked about before, aliasing at multiples of the PRF. To reiterate, 2 targets with Doppler frequencies sampled by an integral multiple of the PRF are indistinguishable in and alone, given that set of pulses. But we can do things to deal with it. We'll get to it in a minute. Now let's look at another issue, and that's blind speed. And what I'm talking about are, again, this is another pictorial issue of the samples, a radar echo from target 1. Here's a radar echo from the target, and here's another radar echo from the target. The blind speeds result from the PRF is equal to the multiple of the Doppler velocity. And here it just shows you out that the unambiguous velocity that you have is n times the blind speed, which is just this quantity here. The Doppler velocity of a target with a Doppler frequency f sub d is lambda over 2. So you put in the PRF and then you get the unambiguous velocity equal to n times the blind speed, which would be, in this case, if we transformed the Doppler axis into velocity, it would be that one cycle of the PRF. Now if we plot the first blind speed as a function of just the PRF, we get these set of curves, again on log-log scales. And that just shows that the blind speed is proportional to the PRF. And if you remember, the unambiguous range was proportional to 1 over the PRF. So what we got is, can't have our cake and eat it too. So we add to the graph, first of all, the physical understanding, the unambiguous range, which is related to the PRF, and we put in the numbers. And when we combine these two, solving, looking at, solving one of the equations for the PRF, plugging it in the other, what that yields is that the blind speed goes as 1 over the unambiguous range, and it's function of the wavelength and the speed of light linearly and divided by 4. And as the example I showed you, we've got a blind speed of 120 knots in an ASR 9 with an unambiguous range of 60 nautical miles, and that's shown right here. So this will constrain the PRFs we choose in our waveforms, the ranges which we measure targets unambiguously, and also the frequencies we build the radar. Because we can be frequency bound. The simplest one is in a fighter aircraft. It's got the order of magnitude of 3 or 4 feet in the nose, and they put radars in the nose to see the bad guys up ahead. And you can't put more than that much aperture, a meter or so of aperture. And to have half decent angular resolution, you want angle. Angle is related roughly to lambda over d. It points to X-band or higher if you're going to put a radar in the nose of a fighter. So you can see how what we're talking about are factors that come into strong play in the design of radar waveforms. Now, there's another factor that has to come into play. Digital technology, I'm going to go over it rather quickly, but digital technology has arisen to the point where the digital portion is such a small fraction of the cost of a radar, you could implement both the I and the Q channel without much problem. But in many radars in the past, people would just implement the I channel or just the Q channel. They're related by a sine theta is related to sine theta, just add pi over 2. But the point is, say we took and we had returns at A1 at the sampling rate, A1, A2, these are our samples we took, A1, A2, A3, A4, A5, A6 with the I channel. And then with the Q channel, we took B1, 2, 3, 4, 5, 6. So then say we subtracted just the A channel adjacent pulses, we get 0 in 2 of them, and we get non-zero terms in the other 2, which would allow us to do some MTI processing. But we're losing information. And say down here in the Q channel, the same thing happens. We're losing about half the information because we're only using one of the two. The way you solve it is radar should be, and they are today mostly pretty much implemented with I and Q channel. So the PRF is twice the Doppler frequency of the target signal. And the phase of the PRF is such that for the I channel, samplings occur at 0 crossing. However, the Q channels, we recover everything, showing the need to implement both channels. Now on to the MTI improvement factor. This is a very, very important definition. You know, it's one of those things that people who work with radars that see into the ground clutter need to put in their heads and think about it and get it. How well, this is the way we measure in the world of Doppler radars, how well we can see targets in clutter. Note that the signal in to the processor and the clutter in per pulse are up here, defined, and the signal out at a specific Doppler frequency and the clutter output at a specific Doppler frequency are defined here. So the MTI improvement factor, which we define as the signal to clutter that comes out divided by the signal to clutter that goes in, is a direct function of the Doppler that you're talking about. So you could have, if you get rid of the land clutter, say in this case, you notice that whether you see this aircraft depends a lot on how well you're able to reduce land clutter or rain clutter. And this is relative power. And this is made up of, intuitively, how much you attenuate the clutter and how much is the signal gain. And that is the number of the number of pulses that you're coherently processing. That ratio. And what you're going to do is each individual MTI filter or pulse Doppler processor will have an MTI improvement factor, which should be plotted as a function of the Doppler of your target. Because the clutter is going to be different in different places, the targets will be different, and so it has to be measured, calculated, and that you quantify it as a function of Doppler. Okay, now we're going to take a break here,